Now we're going to apply the principles of the last PowerPoint and see how they really apply to the real world in terms of all right, calculating uh, concentration, equilibrium concentrations from equilibrium concentrations. So K from equilibrium concentration. When all concentrations equal are known, uh, the mass expression is related to Kc. Two common types of calculations. Given an equilibrium concentration, we can figure out the K. Given the initial concentration, final concentration, we can calculate equilibrium concentration of other species, and then calculate K. And you'll see what we mean by that as we do examples. So here's an example of N2O4 going to 2N2. You start out with a certain amount of reactant, and we could change this to molarity. So it's 0.0350 moles per liter. That's be its molarity. If you think about this is before it's at equilibrium, so your Q at the beginning is that there'll be no product, and there will be all reactant, or 0.035 squared. Okay, right. So the reaction moves to the right to make some product, and then when it does that, it'll finally get to final concentrations. And then to figure out the equilibrium expression, you do product over reactant. Don't forget the exponents, and then you get this, and then you just do the math. And you can see this reaction says there's less. This 10 to minus thirds tells you that the ratio to product, reactant to product to reactant, you could rewrite this 10 to minus third as 1 over 10 to the third. So there's for every one product, there's 10 to the third reactant. You kind of can think of it that way, and there's more reactant at equilibrium than there is product. And you can see that this is 0.03 and this is 0.1. Okay, it's not exactly this value here, but you get the same kind of connect. Right, do another one, just 2A to plus B going to 3C. We know the molarities at equilibrium, so we plug them in. So it's product over reactant. Don't forget the coefficients, cubed, squared. And so we end up getting, what is that, 27 divided by 4, which would be D. Okay, so there's more product and reactant. Okay, and that's so, you might say there's equal amount on both sides, 2 and 1 and 3, but there's 3 times 3 is 9. Over here there's not. Okay, so you don't have to worry about that, but the idea is to know that this number, okay, is the exponent. This exponent is greater than as a positive exponent, and that means there's going to be more product and reactant. Okay, for this reaction system, we know what Kc is, and a system at equilibrium has the following concentration. What what we're going to do is we want to solve for SO2. Right, so you write the equilibrium expression. So product over reactant, okay, and then this rearranged equation for SO2. You get that. Okay, and then plug all your values in. Everything goes here. And do the math, and then take the square root, and you get square root of 1.633, which is, I believe, 1.28. Okay, so calculated Kc from the initial and final concentrations. Here's our equation, and we know we have 1 mole of SO2 and 1 mole of water and 1 liter. So let's figure out the molarities. And here's our molarities. Okay. Okay. So our initial is that we have 1 molar SO2, and when we start out, and there will be no SO3. Also, it's 1 molar oxygen. So that's our initial. So our initial is we have some reactant and no product, and the concentrations are 1 molar, and 0. And if you do the Q, you can see that Q is less than K. It will be equal to 0, and the reaction will move to the right. Okay. So what's going to happen is the reaction is going to move to right and make some SO3, and as it makes SO3, it's going to remove some SO2 and O2. So at equilibrium, what you've done is that you've produced 0.295 molar of this. And where that came from? It came from over here. So what we're going to have to do is, and this is at equilibrium. So the equilibrium expression is going to be a product over our reactant. So our product value would be 0.2925 squared over the amount of SO2 squared times O2. But we don't know the final amounts of our reactant. Okay, but we can figure it out because we know that some of both of these went into this. And so what we're going to do next is something you're going to be using for the next 2 or 3 weeks. Is this thing called the ICE table. And so we better get used to it because it's going to be a very powerful tool that we're going to use here. And then when we get to acids and bases, and then solubility. All right, so get used to it. So we're going to write this thing called concentration table, also known as ICE. And you'll see why in a second. Okay, it's because you have your initial, you have your changes, and you have your equilibrium concentrations, ICE. And so what we're going to do is end up writing a table, showing a table how that works. So let's just go and see how it works. All right, so here's our ICE table. So you have your initial concentrations. Okay. And then you have your final concentration of your SO3. So what you know is that this increased. So this increased by 0.295. Now, if you look at the ratios, for every 1 of SO2, you make 1 SO3. So that means is that the change in SO2 is the same as the change in SO3. So the SO2 had to go down by 0.295. So its concentration went from 1, dropped by 0.925. So remember the reaction's moving to the right, okay? Now the O2 also is going to drop, but it's not going to drop quite as significant because for every 2 of SO3, there's only 1 oxygen. So it's only going to drop by half. So 0.295 divided by 2 is this value here. And then to figure, so I use this number to figure out these numbers. And then I use these numbers to figure out these numbers. Right, and then what you do is you figure out how much of your equilibrium. Okay, so 1 minus 925 is this. 1 minus 462 is this. And we're given this. So now what we have are our final equilibrium concentrations. And then we can plug them into our equilibrium expression. Pay attention to what we did here. This is pretty powerful. All right, so what we do is just plug in our final equilibrium values. Here and here, and here is your answer. Okay. Now, what are the units? So let's, we've been kind of sloppy with units here. So this is going to be molar squared. And this is going to be molar squared cubed. Okay. So this answer is going to be molar minus 1. All right. So the ice table is going to be important for a lot of things here. So we want to have the concentration moles per liter. So if you're just given moles, you have to figure out because it's a concentration. That's because it's relative values. Okay, so and we have to decide which way it's going to go, and that'll be important as we go along. So so if you're just given amount of product, you're given a reaction, and it's not at equilibrium. Let's say you're given R to P, and you're given like 8 of these, and then 3 of these, and the equilibrium constant. First of all, you figure out Q, and if Q is less than K, the reaction will go to the right, and then if the other Q is greater than K, then the reaction will go to the left. So that's the other thing. So maybe you'll give a reactant and the amount of product. You have to decide which way the reaction is going to go first, and then you will have to you can use the ice table. All right, so calculate X equilibrium and the equilibrium value of X concentration from Kc and the X initial. All right, so we'll see what that means here. When all concentrations no but 1. So we have this chemical reaction here, the combustion. So 1500 degrees C, the Kc is 5.67. That means there's going to be more reactant in the product. Just keep that in mind. So the equilibrium mixture of gases had the following concentration. So we have 0.4. We have 0.8. And we have 0.3 here. And at equilibrium, and we don't know what X is. So okay, so hopefully you'll see this is fairly simple. We just have to write the equilibrium expression. And then okay, so no ice table for this because nothing's changing. So everything's at equilibrium already. So just rearrange the equation for water. And so this is your equilibrium expression. Rearrange it for water, and then plug everything in. All right, calculated X equilibrium from Kc. Initial concentrations are given. Okay, so we're going to do an ice table for this one. Okay, so first of all, here's our equation. It says I have 1 mole and 0.5. So first of all, make sure you will have to change that to a molarity. So 1 mole and 0.5, it will end up being 2 molar of both these guys. And it's also assuming that we have no product. Here's the equilibrium expression, and we know the Kc. So we're going to use all this information to figure out what do we want to find here? We want to find the equilibrium concentrations of each one of these guys. All right, so let's do this problem. So we know the initial concentrations are 2 molar, and no molar when you start. Now, when the reaction will go to equilibrium and move to the right. Okay, yeah, because you don't have a product. So we're going to say the H2 is going to decrease by a certain amount to make your product. The amount of I2 is going to change by the same amount because the ratios are 1-to-1 molar ratios. And the increase in HI is going to be twice that amount because of the ratios. All right, so your final concentration is going to be 2.00 minus X for H2, same for I. And the concentration of HI is going to be 2X. Now, if you plug this into our equilibrium expression, okay, which was HI squared over H2 times I2. So HI squared, 2X squared, over 2 minus X squared, and you get this right here. Okay, it's kind of messy, okay, because you got squares. Okay, let's see what we can do. We want to solve for X. And then once we solve for X, we'll plug X back in here to figure out their equilibrium. All right. So if you notice, both of those guys were squared. So if you just take the square root of both, you'll end up with the 2x over 2 minus x, and therefore you have to take the square root of 55.64, and so you get this expression right here, and then expand it, and then multiply it out, and then I get like terms, and then divide both sides by 9.459, and so the x, which is the change, is going to be 1.58. So we plug that back in. Okay, hopefully you saw what we did here. So this is from the previous. So the previous slide, it said this value right here, 2x squared over 2 minus x squared equals 55.64. And then because both of these are squared, and you take the square root of it, you'll get 2x over 2 minus x, and the square root of 55.64. Okay, plug the 1.58 in, so minus 1.58, minus 1.58, and double that here. And so you get 0.42, and 3.16. And these are the final concentrations of your species. And then you can plug those, and that's it. All right, another problem here. 1 mole of H2I2 HR placed in 0.5 liters. What are the equilibrium constants, concentrations of H2I2 and HI? All right. First of all, so write the equilibrium expression, and also figure out your initial concentrations. Now, in this case, is going to be different because you have 2 molar of all of them. Okay. So first thing you're going to have to do, so you don't know if the reaction is actually going to move to right. This is because you got product. Okay, so first thing you have to do is figure out the Q. Okay, and then if there's too much product, okay, or if Q is greater than K, greater than 55.64, the reaction will move to the left. Okay, in that case, you'll be taking away product and moving it to the right. If the All right, so let's see what we got here. So here's the equilibrium expression, and essentially it says there's 55 products to 56 products to one reactant. You can think of it like that. It's not exactly right, but it's a good way to kind of think about it. 55 to 1 ratio, sort of. So what you need to figure out is Q. So the initial concentrations is you have 2 molar of each, and you're using this equation, so it's going to be 2 squared divided by 2 times 2, and equals Q equals 1. So you can see that the ratio of the reactant products 1 to 1, which is a lot less than 55.64 to 1. So there's not enough product here. So it needs to make more product. So the reaction is going to move to the right. So what you're going to do is you're going to see a decrease in the 2 reactants and an increase in the product. All right, and so let's set it up. So here's your initial concentrations. Okay, and they change by x, minus x, down minus x, up by 2x. All right, and then the final concentrations are, in terms of x, are like this. Then you plug them into the equations. I plug them into our equilibrium expression that we had on the previous slides. And so notice we have squared here. So if we take the square root of the equilibrium constant, we'll end up getting this here. And let's continue. All right, and then you take the square root of both sides, and you get 7.4959 is equal to this. Then you write out the then you expand it, further expand it, and then do your algebra, and then you get x is equal to 1.37. Okay, so it's just simple algebra from here to here. All right, then what you need to do is put the 1.37 back in the equation. So the H2 and I2 are both going to decrease by 1.37. They start at 2, so they go down to 0.63. And then the final concentration of the HI is going to be 2 plus 2x, or 4.74. And if you want, what you should do is really check your answer. So what you should do is take this 4.74, put it back in the equilibrium expression, 4.74 squared times 0.63 times 0.63, and it should give you your 55, whatever it was, 55.6. So let's do another problem here. Given these 4 choices, and let's see which one it is. The initial concentrations of moles is that you're given reactant, but you're given no product. You're given Kc and 250 milliliters, which is 0.25 liters. So the first thing you need to do is find out how many moles of these are. So take 0.25 divided by 0.25, and you'll have 1 mole of each one and no moles of this. Okay, and what you want to do is find out what are the equilibrium concentrations of all these guys when you're all said and done. Okay, here's our initial equation. Here's our initial concentrations. The reaction is moved to right, so you lose some of the reactant. It goes up by 2 because of the exponent here. And so your final concentrations are here. Okay. And then we have, so you have your equilibrium expression is going to be NO squared over N2 times O2. Okay, so we're going to, and that equals 0.0123. Okay, so this here is from the previous page when we had the 0.0123 is the equilibrium constant, and that equals to product NO squared over N2 O2. So the equilibrium expression is right there. So we replace these values with the values we got from the ice table. And we say 1x squared. Actually, it's 1 minus x times 1 minus x, which is 1 minus x squared. That's why. So we simplified it there. And we can see that both squared. So if we just take the square root of both sides, we can get these squares off of the x's. Okay, then expand. Okay, so and then solve for x. And then we get x is equal to 0.0526, and then plug those numbers into our initials, and so the okay, then that's how you get your answers. Okay. All right, so here's another problem. Take some acetic acid plus ethanol and make ethyl acetate. Okay. The K is 0.11. The initial concentrations of each of the reactants is 0.81. It's heated to 100 degrees C. And what are the concentrations at equilibrium? Okay. So we're going to have an ice table, figure these out. So first thing to do is write the equilibrium expression. Okay, so here it is, product over reactant is equal to 0.11. And then set up your, so we're going to want to find the, we know the initial concentrations of these guys and this guy as well. There's none of this. And then what we're going to want to do is find out our final concentration by seeing how much it changes by. So we're going to use our ice table to do that. Okay, so really pay attention what we're going to do here. So here's our initial concentrations. Goes down by minus x, and plus goes up by x because they all have the same coefficient. Right, so final equilibrium is going to be 0.181 minus x, 0.81 minus x. That goes up by x. So put those into our equilibrium expression. All right. Okay, next thing you got to do is that you got to take this equation and solve for x. So on the next slide, what we're going to do is show you the result of the expansion of it. So what you're going to do is you're going to multiply these two terms together using, you know, you could use, remember using FOIL and all that, simple algebra you learned in 8th grade, I guess. And then multiply the product of this side and put it over here. And that'll equal x, and then you'll have a quadratic equation. And that gets kind of messy, but you know it's a quadratic equation. You know it's a quadratic equation, so there's ways of solving quadratic equations. All right, so let's go to the next slide and see how it expands. This equation expands. And you can do this on your own and see if you get the right answer. So why don't you go ahead and do your FOIL, 0.81. Right, and here's what we get. So So this is the FOIL of that, and then you multiply both sides by that, and you get this. All right. Then what we're gonna do is get this x over here, and then what we got is this equation. And then you could just, like terms, you got x here and x here, and so you end up with this guy right here. Okay, and if you rearrange it, you'll see that you can get it into a quadratic form. Okay, now, and then what you want to do is solve for x using the quadratic formula, and you could use this, okay, or there's programs out there that you can just, and I kind of like those instead of doing the rigor here. The rigor is always good, but you could, it might be even on your calculator, you can just solve for x. Now, one of the things you're going to find is that you'll end up getting two values for x, and what you're going to have to do is decide which x is the one that makes more sense. All right, so go ahead and solve for that's why is that, because you got a plus and minus here. So we're going to go ahead and solve for x, and we'll get two x's, and then we'll see which one makes sense. All right, hopefully you see what we've done here, how we're doing things. Okay, so here's quadratic, and you get so here's when you get done, and then you end up with two values of x. Okay, now which one is going to be which one is going to make sense? Okay, well, if you go back and look at what we did, I mean our two equations are for our reactant. The reactant was 0.810 minus x, okay? Now, if you put in 10 minus 6, you end up with a negative number, and you can't use, and it can't have a negative concentration. Well, you could. That just means the reaction is moving the wrong way. But we already determined, know which way it's going to move because we don't have any product. Okay, so we're going to use this value here, and to figure out our final concentrations. Okay, so if we use 10.6, it doesn't make any sense because you end up with a negative concentration. Right, and so we go ahead and plug it back in, our x values, and get our final concentrations. And there you go. All right, now we're going to figure out the equilibrium of a concentration from our initial concentration in Kc. When Kc is very, very small, 10 to the minus 18th. This means there's hardly going to be any product. There's going to be way more reactant than product. Our initial concentration of water is going to be 1.1 molar. And what we want to do is find out what our final concentration H2 at equilibrium. Okay, so we write the equilibrium expression right here. So you always do that if you're given it. Okay, and then we're going to do isotable. Now we're going to assume something here because this number is really, really small. Okay, so the reaction's going to move to right because you don't have any product. And so 0.1, and so you have 0.0 and 0.0. So there are different ways you can look at this. You can either say, so you can go 2x, so it goes down by minus 2x. And the other side goes up by 2x and plus x. So the final concentrations are going to be 0.1 minus 2x, 2x and x. All right, so and then what we do is we plug everything in, and we get so we get it's h2 squared times the O2, so it's going to be 2x squared times x. So this is squared, and this is x from the equilibrium, times this squared. Okay. All right. Now, and then you can expand it to look like this up here. And you can see that this is going to be really messy. It's a cubic equation. And you could solve it. There's ways of doing it. There's calculators and things. But these days do it. But, you know, back in the day, before we had all these calculators, we figure out things using our brains and try to assume some things. So if Kc is very, very small, the change in x is going to be very, very small. All right. So this value here is going to be negligible right here. This is going to be negligible. So what we can do is just kind of throw it out. Okay. And then what you end up with is 7.3 times 10 to the minus 18th equals 4x squared over 0.1. And then what we can do is simply solve for x cubed by taking the cube root. Okay, so typically, if well, we'll see. There's assumptions here, but if this number is very, very small, very, very large, very, very, very small, then it's hardly going to have any change at all on this concentration here. And kind of one way to do is if this number here is like 1/1000th of this value here. Okay, so if this number here is 1/1000th or less than this, then your concentration, then you're okay. All right, so you can see that this is 10 to the first, this is 10 to the minus 18th. This is far less than 10 to the third in terms of its difference. Okay, so we can make that assumption and move forward. Okay, so simply there's our equation right here. Okay, so multiply, get rid of that 2x term, and so you get this right here. Then solve for x cubed. And you get 4x cubed equals 7.3 times 10 to the minus 20th. And then take the cube root of that. And then you get x is equal to 2.76 times 10 to the minus 7th. Okay. And you can see x is very, very small. And that's kind of what you expected. Okay. We said it was going to be very, very small. All right, and then what we do is we just go back and plug it into for H2 and O2. All right, we won't need to put it back into. We just want to find the H2. So the H2 was 2x, so it's going to be 2 times 2.6 times 10 to the minus 7th. And this tells us when we kind of can make that assumption. Here it says that when the concentration is 100 times, I said 1,000. Okay, so you could use 100. All right. So we had in the previous example is 10 to the I forget what it was, 10 to the minus 18th or something, and then our concentration was 10 to the first. Okay, this number here is much greater than 100 times this value here, so it's okay to make that assumption that x doesn't have any effect on this here. Okay. All right, so let's take a look at another one. So we have a 10 to the minus 16th, which is a really small number. right, we place 0.2 atmosphere into container. What would be the pressure at equilibrium? So we know the equilibrium constant is 3.5 times 10 to the 16th right here. Here's our equilibrium expression. Okay. All right. Now, so our initial concentration is 0.2. Okay. And right. And so this is 10 to the minus first. So this value here is 2 times 10 to the minus first. And I'm doing this so I can see if it's okay if I don't include. And so it's going to change by minus 2x, all right? But I want to see if I need to include that into my my problem solving here. So look at this. 10 to the minus first is that 100 times greater than 10 to the minus 16th? Yes. So what I can do is I can actually just remove that. So my final concentration of A is simply going to be 0.2. Right. So then your equation is going to be B over A squared. So X over 0.2 squared. And then solve for X. And you get that. Okay, so make sure you get that. All right, so the equilibrium expressions 10 to the minus 16th. The ice table says is that the reaction is going to move to right because you don't have any product. Okay, you have 0.2 atmospheres here and 0 here. All right. So how much is it going to go down? It's going to go down by 2x, and the other side is going to go up by x. But because this change here is much less than our concentration, it's going to have hardly any effect, and we can cancel it out. So if we actually want to include it, and you could, and you'll end up getting a number that's similar, probably the same because of sig figs. So if you did include it, it'd be 0.2 minus 2x. 2x really doesn't have any effect on it, so we can just assume it's 0.2. Okay, so that's when K is very, very small. You can make these kind of assumptions. And you'll see it again when we get into acids and bases and solutions. Okay, so this ends equilibrium introductory, and you're gonna see plenty of this in the next couple sets of material. Like I said, acids, bases, and insolubility. So similar things using the ice table and the equilibrium. So there'll be practice problems that you'll have to work with. Now, so there'll be practice, and you have to go back over these to use this as your source, and you could use the book as well. So the key things, well, whenever you have a chemical reaction, A to B, and we know we'll go to equilibrium, all right, is that you can write, first of all, you can always write the reaction quotient and the equilibrium expression. So Q will be, remember, both of them are going to be product over reactant, and you have to include the exponents as well. And if you're using with concentration and pressure, it's different. But you use the same idea. Now, so the other thing you would like to have, and you don't necessarily have to have it, is the equilibrium constant. Now, if you don't have the equilibrium constant, you have to figure it out. And that means you have to have the equilibrium values of A and B to solve it. But typically what we want to do is find out how much B or A there is at equilibrium, all right, from an initial concentrations, okay? And so you're going to be you'll have the equilibrium constant and then you'll be coming up with the ICE table to figure that out. So so I mean the steps would be always given an equation, write the reaction quotient and the equilibrium expression, basically the same thing. And then if it wants the equilibrium constant, you have to have A and B already. All right. Now, if you want to find final concentration, equilibrium concentrations of A or B, you will be given equilibrium constant, and then you'll be to help you solve for that. And then what you'll do is you'll use the ICE table to change an A and B to figure out how much they change by. Okay. Now we just did this for one problem is that if you're given both reactant and product, in most of the values we started with a certain amount of reactant and no product, and the reaction that we automatically assumes goes to the right. But sometimes you're given both reactant and product, amounts of reactant and product, and so you have to figure out Q and determine which way it goes. Now, in all the examples we had, is that we saw a reduction in our reactant and increase in our product. Now, for some reason, the reaction was actually, there was more product than reactant, and the reaction would move to the left. Okay, you would see the opposite. You would see a decrease in your product and an increase in your reactant, but still by using the coefficients. Right. So there was several problems that use these. Try to put them in proper perspective as you do them, and I'll give you worksheets, and you'll be given a test on this. All right. That's all for this, and good luck.